Inductors and reductance reactants. So we're going to move over to Eli. We'll discuss the basic structure and characteristics of inductors, discuss various types of inductors, analyze series inductors, parallel inductors, analyze induced DC switching circuits. So we'll look at what we call charge. We can use these things also to create time constants too, the LR time constants. We'll look at that. Analyze some inductor applications and test inductors. So basically, inductor is nothing but a bunch of turns of coils of wire. And what happens so if we put DC on an inductor and let it charge, and we'll show you charging too, then it's nothing but a bunch of wire. And the only thing that would limit the current, of course, is the resistance of the wire. So these are inductors. These are all bad, by the way. So basically, if I put these things up, so we should be able to check these things with an ohm meter. So if you check these with an ohm meter, they all measure infinity, so that means they're open. What happens with these is that we don't like to really use these because the wires are so small, and you can actually, if you look real close, you can see where they are attached to. So they're wrapped around a ceramic spool. If I can get this thing to focus. And that little tiny wire comes over here and it solders onto that. And what happens when we get these things out in lab, they break that little wire. Very, very small. So a quick check for an inductor is just to measure with your ohm meter. And of course, it's not going to measure zero. It depends on the size of the inductor. It'll measure the resistance of the wire. It's usually fine gauge wire. It's magnetic wire because we really want the wires really, really close together. Most of your inductors are better than this don't mean it's the resistance. So this is an inductor, but they encapsulated this with epoxy, and these are the inductors that we'll be using. So you can't. So these are called radial leads. So leads that come out the bottom or one side of a component are called radial leads. And if they come out to two sides, they're called axial leads. So radial.
Radial.
And if it comes out the sides, it's called radial. It's called axial leads. So if you think about the axle of a car, that comes up. So this will be an axial lead right here. And that's something you need to know when you order them, right? Because the replacement is pretty circuit board, and you buy the wrong one, then the one you buy won't fit, or you have to stretch the wires in. So these right here are pretty reliable. They won't, if you put a lot of DC across them, they'll burn them up, but AC, you shouldn't have any problem. So this is the symbol of an inductor. And what determines the inductance, of course, is the number of turns of wire, how close you get them together, and then the length of the wire, and then what do you wrap that thing around? We have air core, or we have different ones that we have to actually set the cross-sectional area, how close we get them. So basically, this is an inductor. So an inductor will never be just a 0 ohms. So this is the equivalent circuit right here. So it's got a resistance of the wire connected in series with the actual inductor itself.
What exactly is this?
No, we'll put these things in an AC circuit. If we put them in a DC circuit, the only time we'll ever put them in the DC circuit is if we want to use them as filters. And then we got to be really, really careful because you're depending on XBAL. So your stereo speakers are inductors, but they don't burn up because we don't put DC across them. If you put DC across that 8-ohm speaker, you're going to burn it up. So they get their opposition from AC. Yeah, if you got some, these big old woofers, then those things will have almost no. If you measure the resistance across that thing, they'll be about six ohms. If you put 12 volts across 6 ohms, right, you understand that's going to be almost that's going to be 2 amps across that thing. But we're not putting DC on them, we're putting AC on them. So audio is AC. I used to have a radio up that I could get across the speaker, but all I've got is a little. So we can use speakers as microphones, by the way. So the way a speaker works, it's got a magnet, and then it's got a diaphragm attached to it. And then it's got a coil that we put around this. And this is inside a sleeve. So this is, when we come over here and these start going plus and minus, it's going to cause it either to retract or repel, and it's going to move up and down. It moves the diaphragm, generates sound waves. Well, if I come up here and talk into this, and I come over here and move this magnet right here, and it cuts across these wires, then it's going to generate an EMF because that's everything I need, right? You understand? So I can use a mic. I can use a microphone I can use a speaker as a microphone. So let me switch cameras. And of course, I got my mic. It's not real good. So here's my speaker. First, I tap this thing. If I talk into it, you can actually see that sound waves are AC. You'll see it? So you hard to actually see audio because all your basses and all your trebles and mid ranges, they're all summed together, so it really looks strange. And then you come into your speakers, some of your speakers will have little grooves in them, and each one of these are actually resonates at a certain range of frequencies. So down here might be your highs, and out here might handle your bass. It's really neat. And then your really good speakers, you use capacitors to set up filters to let certain frequencies go just to those speakers. Those are your better speakers. If y'all have ever tore any car speakers across, a lot of your really good car speakers will have a bass, and then up in here they'll have another speaker actually mounted in the center, and then they'll have a capacitor in there to split them up to filter them out. So you only let a range of filters frequencies go to each speaker. So Faraday's law says the amount of voltage induced into a coil is directly proportional to the rate of change of the magnetic field with respect to the coil. Now, Lenz's law says when the current through a coil changes and an induced voltage is created as a result of the changing magnetic field, the direction of the induced voltage is always opposite. So this is what's happening, is we got these things coiled together. So when I put current flow through this one, this might create it comes out like this. But when this comes like this, there's another coil right beside it. So it's coming out of this one, and it's going to cut the wire right beside it. Well, if it's going this way and this one, it's going to try to induce a voltage going that way, which is going to try to oppose the voltage in the coil beside it. So this is the way an inductor works. If we put AC on that thing, these things are constantly trying, the coil beside the previous coil is trying to oppose the current flow from the coil before that. So these are the two laws. Of course, we know that. So these are symbols. We have, I have some, let me find my thing over here. So what would I do if I don't have an adjustable capacitor? What would I have to change? I mean, an adjustable conductor. What would I have to change?
The inductor would be core material.
Could change the core. Could change the size of the core. Could change the number of turns. That would be hard to do. Could change the length. So the most popular way is to adjust this guy right here. So these are some variable capacitors. And what we're doing is we're adjusting the core on both. Unfortunately, this one right here got broke. Now when you adjust it, it's non-metal. So you a pair of plastic. That whole thing.
Oh my.
So what happens if I put DC across this thing, it acts like a wire. But it don't like to change. So the instant I put DC on this thing is going to try to block that current flow. Because as soon as you put that DC, this guy right here is going to have current. It's going to induce a voltage into that, which imposes the current. So if this guy's going this way, this guy's going to try to go the other way, right? You understand that? So the instant you put DC on this thing, it's going to try to oppose it. But once the opposition steadies out, then it's going to act like a wire. So we can get a time constant out of this. By the way, these are these guys. Let me pass these guys. So just because you got a color code, all of these guys are different colors. Not a follow when you turn it on. Well, the thing is, like, with the color code value, you make the problem zero alone. Just because you measure infinity on the color code, I'll find the color code for the master, but notice the actual colors are the same that you learned in DC. So black, brown, red, orange, yellow, green, blue, violet, gray, and white. My big, beautiful roses occupy your garden, but violets grow wild. So the color code is exactly the way, and that's the way we would read this. So that would be a 4, that would be a 7. And then we got to figure out what we do with that. Well, if we got a gold is we're going to divide it by 10, and it's going to be in micro, it's going to be in, by the way, these guys are rated in units called henries. Yeah. So capacitors are rated in what? Farads. These guys are rated in henries. And the symbol we use to represent them is L. We can't use I because I is already reserved for current, right? You understand? So L. So yeah, for inductor. So when we calculate opposition, it's going to be X of L. We calculate the opposition for it in AC circuit. In a DC circuit, it's just gonna act like, once it charges, it's gonna act like a conductor.
So we're gonna have microhenry.
Microhenries, that's what this is, a microhenry. I ain't never seen a picohenry.
Oh, no people.
I'm not saying they are. I've never seen one. So what's that one? What's the first color? You know, first color can't be a black. It's a red. It's a red. So that's a what? That's a 2. What's our second color? Purple. Probably purple. What's the next color?
Black, yeah, red, purple, black, gold.
Okay. And then gold, so we'll move that over. So it looks like it's going to be a 202.7 microhenry.
So you can put H to Henry.
Yes.
L.
L is what we're going to put in circuits. So if I have an inductor in a circuit, it's going to be labeled like L1, L2, L3. And of course, you'll have R1, R2, R3. Capacitors are going to be labeled C1, C2. Go ahead.
They're always micro.
No. We're dealing with this guy right here. And I hadn't figured out this yet. I know what this is. So this is 100 millihenries. So they're usually in millihenries and microhenries. In henries, we have this right here. I'll have to show y'all that when we go next door. Oh, I can go get it. Henry. So this is not a transformer. This is something that looks like a transformer. It's only got 2 wires. It cannot be a transformer. A transformer will have to have at least 4 wires on it. So this is an inductor. This is a 7 Henry inductor. I guess I could have put it in front of that camera. Yeah, so this is 7 Henry. I'll pass this around. This is the one we'll charge up. This makes it show things like that. All your relays are all your transformers show current. Motors have to. So that's 7 Henry right there.
So, again, how do you calculate whether it's milli?
Well, these little guys right here are going to be microhenries. These guys right here are going to be millihenries. Now, unfortunately, we don't have. We don't have a meter that measures these things. Now we can set up a circuit, but to set up the circuit, so this is what we'll use. So if I can come up here and I can put a 1 kilohertz, if I have a 1 kilohertz oscillator, and I might have that circuit around there somewhere. Using a little timer. We have a timer called a 555. You can use it to time. It's a little integrated circuit, but you can also set it up to oscillate, and it's pretty easy to set up the frequency. Well, if you had a precise frequency like this, so we can do this on our trainers over here. And then I had a 1K resistor, and then I had my inductor. Then we could calculate it, right? So how could I do this? And this was 1 volt. This really don't make any difference. But how would I figure this out? And this was 1K. So this is what I usually use to measure inductors. So how would I do that? Well, I'd measure the voltage drop across this, right? Use that to calculate my current, since it's a series circuit and the current's the same. I measure the voltage drop across that, and then I would calculate X of L, and then I would use that to calculate L. So that's what I would do. That's how I measure with a circuit. So this is not like so normally we have a no-go, like we do with a capacitor. So what's our no-go, no-go check with a capacitor? Well, we put an ohm meter across it, and we see it charged, we say it's good. If we have a 9-volt, if we get these little old tiny ones, we can charge it through a 9-volt battery through our meter on volts, and we'll watch it. We can watch it charge. But that doesn't tell us the size of the capacitor. All it is a no-go. So here we measure this with an ohm meter. If it measures low ohms, it usually means it's what? It's good. If it measures infinity, it means it's what? Bad. So I can't tell if there's any winding short or anything like that. So if a capacitor, if it don't charge up to overload, then odds are it's leaky. This guy right here, that's about the only thing you can check to do this.
So in other words, we're not really checking.
The capacitance. We're gonna take their measured values. But like I said, even me, we don't have a inductive meter here, but we've got these function generators which you don't have. So I can set that thing up to 1,000 hertz, and then that way I can measure it through math, right? Understand? Just like I could do a capacitor, we could use the same circuit to check a capacitor, but you got to have that 1,000 hertz. You got to have 1,000 hertz is good because but if you got any type of oscillator, you could do that. You could use 60 cycle, but that's not good because that's high current out there, guys. If I made a mistake on this guy right here, if you look at it, it's got a 50 ohm resistor in series with it. So if I come up here and short this out, it's not going to hurt that function generator because that 50 ohm resistor will drop it. And why is it 50 ohm? Shorts hurts a lot unless you protect it. So the way our function generator works, it's got a 50 ohm resistor right here. So if I short this out, that 50 ohm resistor drops it. Unfortunately, what that means is y'all probably notice that when you change things, like if you change the frequency, X of C goes down, which caused the total opposition to go down, and probably if you noticed, the output of your function generator went down, so you have to keep adjusting it up to keep that same, and that's because of that 50 ohm resistor. Another reason why it's 50 ohm, and I'm not going to get into that. Well, we'll talk about it just a little bit. In a communication system, to get the maximum power transfer from the source to the destination, all the impedances in the circuit have to match. We call that impedance matching. Coax cable, the coax cable that runs into your computer, if you're on your house, is a 50 ohm cable. All the amplifiers down the whole line is matched to 50 ohms.
You do it like that, you're talking to me now.
Well, if we did the math though, I got a little circuit where we changed resistors. So I have an internal power supply that's got 100 ohms, and we start changing the load out, and you find out when I put a 100 ohm resistor out there, we get maximum power transfer to the 100 ohm, and that's called impedance matching. Network cable is a 100 ohm cable, so that means at 100 megahertz. So 100 megahertz, which is the carrier, that cable represents 100 ohms. And that's not including the ohms per, that's the reactive ohms and not the ohms of the cable. That's one of the reasons why the cable lengths are limited. So like Ethernet is 100 meters. If you go over 100 meters, you got to go through some type of repeater to get, because now you're dealing with the resistance of the cable. So that's 50 ohms, so I could play around with a 50 ohm coax cable with this function generator, and I would have impedance matching. So if I was testing out a coax system, but it wouldn't work on the Ethernet cable because that's a 100 ohm cable at 100 megahertz. So, how did I get off on that? Oh, why does it have that 50? But that 50 ohm resistor allows me to short the output off without blowing a fuse on that guy right there. But don't do that at your house because there's no protection on your house. Even though I've seen people do that. I've seen electricians literally short out a plug so they can figure out what circuit breaker that plug is on. Because unfortunately, y'all don't do this, but you'll go into a house and you're going to go into the panel and it's going to have all these breakers on it, and they got all these nice little labels beside them, and none of them's going to have anything filled in on them. Almost no electricians that wire houses fill in those breakers, even though they wire them. And that would be so easy. So you go in there to your house, and you got to figure out, you're going to work on a light fixture, and what do you have to do? You have to go in there and start clicking off breakers so everything goes off. But I've literally seen people go out and deliberately short out something to pop the breaker so they don't have to do what? Figure out, go ahead and start tripping off everything and figure out what shirts off.
Or you turn off everything.
Huh?
Or you turn off the turn.
Well, you could, but now you kill your whole house. I mean, your plant would not like you to kill the power to the plant just because. Now in a plant, odds are they're all going to be labeled. But when most of the time when an electrician comes in and wires a house, these electricians wire their house, they don't take the time to label those panel boxes.
I mean, climate's a little tool you can plug into an outlet. If you're trying to turn off an outlet, you plug it up and then it'll tone the breaker.
Yeah, you have a little toner that you can go in and run down and it'll beep on the breaker.
Well, like when I'm changing a light, I mean, what to do it, I usually turn the light off. If it's a light that's, you know.
Well, lights you can do that, but base plugs, because base plugs wear out, guys. So base plugs should never get warm. If you got a base plug that's getting warm, you need to do what? You need to change it because they get resistance, especially plugs that you use a what? You use a lot. The base plug is these outlets right here. They call them base plugs because they're down usually toward the base of the, and they're not supposed to get hot. So if they're getting hot, there's got to be a watt in there somewhere. There's got to be an R in there somewhere where there shouldn't be an R. So I keep a box of those things at the house all the time.
Oh yeah, they're cheap too.
Yeah, they are. For a box, you go down to Lowe's and buy a whole box. But make sure you buy the right ones. Yeah. Like these are 20 amp plugs. They got a little notch on the side. And these should have 12 gauge. They should have 12 gauge wire runs. So don't go out and buy a 20 amp plug so a 20 amp plug cord will fit in there. So this is not some old stuff, guys. But both of y'all are in the electrical trade, and that's something y'all need to know. So if you ever go out there and get the opportunity to wire a house, mark those breakers. All it takes is an instant just to put where these, yeah. But they don't do it. They just don't take that time. So this is what we'll use. We can use this to measure that. In fact, these, I cannot figure out this rating on here. So 410. These are 100 millihenries. So I hooked up this exact circuit and figured out that it was. So I don't know how that goes. Huh? Yeah, but that's the labeling on it. So the labeling on it is 410. Now what does 410 have to do with 100 millihenries? And it's 100 millihenries. So these are the ones that we'll use in lab, by the way, just these. These are nice because we don't have to worry about breaking the wire. Like I said, I've got a drawer full of these that are no good anymore. A variable, like I say, in electronics, any symbol that you see that's got an arrow through it, it means it's variable. And then we have different cores. We have air core inductors. Then we have iron core inductors, and then ferric core inductors. So ferric core inductors is just basically iron shaped or iron dust. And so these are ferric. Huh? No, well, it's got a core, but it's just wrapped around like a piece of plastic or something like that. It just has nothing in there. So I don't have my straw in here. Yeah, so they just have a tube, and then they just wrap the inductor around that thing, and they don't put anything in there. Well, it's going to be wrapped around something, but it's just not going to have any type of metal or anything inside there. And you see a lot of those, especially, the only time you'll probably run into those if you're dealing with really high, real high frequencies. So these are just some pictures. But just because you see this kind of stuff don't mean it's a resistor. That's your problem with it. It could be a what? It could be a resistor, it could be a capacitor, or it could be an inductor. This is why it's important when you get these things to keep them in the right drawer. Well, we know if it's an inductor, it's going to measure almost equal. Because it's going to be way more than micrometers, right? It's almost like a wire does. But when you look at this, it might say, well, it's supposed to be 100 ohms. We don't have, I've never, I've seen it shorted around, but I've never seen it before. I've seen the circuit that the resistance is mounted in have a short circuit. If you measure that and it measures 3 plus 0, if it measures infinity, what you can do on it, you can do if it measures the ohm value, what you do so a basic power supply, basically, we'll start off with a transformer, and then we'll run into a rectifier, and that's going to be diodes, which if you take solid state, which I don't take that, and then we'll go into a filter, which is usually just a nice big capacitor, so we know how that works now, right? And then we might use it that way. Normally after that, we'll run it into a regulator. Now these are the ones the trainer uses. I can show you the schematics on the trainer. This is what they use. Now these guys are extremely hard. They're easy to fix. I mean, so if you got a trainer where the power supplies are bad, and it's real obvious on our trainers that the power supplies are bad, those LEDs on the side either off or they're real dim. Don't put it back up. That bothers me too. And I see that all the time. People come up here to get a computer, and they'll go walking by there, and they'll come back and bring it back up here, and they get another one, and they don't even. And what ends up, if you don't let us know, what happens? Yeah, so that's happened. I've had that happen before. None of these all these trainers are broke. We all the ones that use them. We don't check these things all the time. So if you got one of these trainers that you got a problem with the power supplies, let your instructor know when you bring it in. Don't restore it back in the cabinet over there. Say, Rich, this power supply is no good, and I'll come up here and I'll verify that. So we got everything we need to fix these trainers. Now, there you go. Switching power supply. They usually bring the AC directly in, and then they rectify it, and then they oscillate it. And then they'll come over here, and then they'll run it then they take this output, and they'll run it maybe through one diode. They run it through an inductor filter, and then they sense this, and then they bring it back and run a feedback into the oscillator so they control the frequency of the oscillator. These guys you can't fix. These guys, they're real weird. They're really nice. They're very efficient. They have the ability to work on multiple voltages. So if you ever look at your power supply on your trainer, so an analog power supply, you have to run it on the right voltage. You can't, or you switch it. So used to on the old power supply, in fact, the power supplies we use in desktops, if you look on the back, it's got a switch. You can switch it between 120 and 240. These guys right here, what do? You just plug them in. And this guy right here can run on any voltage between, if I can read it, between 100 and 240 volts. All you got to do if you go to a different country is buy the adapter. So Germany uses these little weird circle things, but they're all 230. These guys are almost impossible to fix, but they're all sealed up. These guys right here, so switch power supply uses an inductor filter and an analog electric power supply uses. And if you take solid state, we'll teach you how to build your power supply, by the way. And these are usually the ones you'll find. I think I've got a computer power supply taken apart. You can see that. So inductors in series, we just add them together, just like we do. So we don't have to worry about that. Normally, we don't worry about that because if we deal with opposition, we add them together anyway. Inductors. So what would be total inductance here? If I do that in your head. Yeah, 9.5. That's Henry, so it would be pretty good size. So all you do is just add them together. Inductors in parallel, we do them just like we do resistors in parallel. So this is where you have to use that reciprocal with some of the reciprocal things. So L, not X of L, would be equal to 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 over all we can go. If you have two inductors of the same size, if you got three inductors of the same size, you take one of them and divide it by the number that you have. That's why. So what would the total inductance be here? So we should expect it to be what? Yeah, but we should expect it to be less than 2 million. So LT would be equal to 1 over 10 milli plus 1 over 5 milli over 1 over 2 milli. So Quinn's already got what? Has a chance of being right. Doesn't mean it's right, but it has a chance, right? So we should expect it to be smaller than the smallest. Everybody got that? We okay? Anybody want to stay at work? Now the biggest problem is people don't hit the equal key when they enter the flat. What do you think? So this is what people will do. I've seen this so many times. Well, your calculator might be different.
Well, I put in the entire thing.
Yeah, you got but a standard calculator. And now I know all of them's in milli, so my answer will be in milli. So 10, and then reciprocal plus 5, reciprocal plus 2, reciprocal, and then what people will do is they'll hit the reciprocal key again right here. Without hitting the what? Equals reciprocal 1.65 minutes. So that's the problem with that formula right there. I used to have a HP or was it 125, which was the first calculator that came out where you could enter the formulas. I used to think it was so cool. But I don't do that because 90% of the students don't have them stuff. In DC circuits, the only resistance is provided by the conductor is that formed by the inductor or the R of the wire. For this reason, the inductor is considered to be a short for DC. Might not necessarily be a short. I mean, this guy right here is a 500 millihenry inductor. If you measure it, I forgot how many ohms it's got. I'd have to find a good one. I think I'm not going to give these out because somebody will break that wire. So this guy's got.
The whole point don't want to put inductors in.
Well, we do, but we protect them with a resistor. So this guy's got 600, so you can't say it's a short. This guy's got 604 ohms of resistance. Because look at the amount of wire and look at the gauge of the wire. So we can't say it's a short. But if you put a lot of voltage across it, it would definitely burn the wire off right here, right? But if I come up here and look at the one that's 7 Henry that I gave you, odds are it would measure really, really low, right? So the number of Henrys, the lower the bigger the Henrys, the more it will act like.
Sorry, what?
The bigger the Henrys, the less the resistance. So this would be what would happen when I first put DC on this thing. These guys hate changing current. So capacitors love changing current. The higher the change, the less opposition. Inductors don't like change. So as soon as we close that switch, if I come over and close that switch, the instant I close that, this thing would have almost infinite resistance. It's going to block that current. And that's why over here we're dealing with what? We're dealing with EI, so current lags. So when we start off, if it blocks it, all the voltage will drop across the inductor, and we have no voltage drop across the resistor at the instant I close that switch. But then what's going to happen as the current, as things stabilizes, and the current the voltage drop across this is going to drop down, and the voltage drop across this is going to go up. And then what's going to be dropped across the resistor will be determined by the wire resistance of the actual inductor. So this thing has a charging curve, just like resistors, but it's going to be just opposite. So one time constant is equal to L over R. And this is going to be that 63% thing. So time to fully charge is going to be L over R times 5. It should be on your formula sheet. Inductors are on the back of your formula sheet.
Actually, the one that you have.
Oh yeah, these are your basic formulas, yeah. So the slowest this thing will charge is when you have no R. The bigger the R, the faster this thing will charge. Because what you're doing is you're limiting the change. So if I put a big resistor on here, it's going to limit the current flow. It's going to limit the strength of the magnetic field that's being induced in the coil. It's going to limit the reverse counter EMF that's induced in the next coil. It's going to cause it to charge up faster. The smaller the resistor, the faster the current comes into this thing. This thing's going to oppose it. So this thing right here hates change. So that means if I put this in an AC circuit, the higher the frequency, the more opposition this thing has. The lower the opposition, the less it has. we could do this, we'll have to figure this out, but we'll have to use a pretty small resistance. So the slowest it will charge will be and we'll have to measure current, guys, because someone, on that 7 microamp, we probably put the current meter in here, and we can actually see it charge.
So what's the difference between, EMC or fiber?
What do you mean?
That's
Oh, this is fully charged, I'm sorry. So when it's fully charged, this guy would be dropping its minimum voltage. And this guy will be its maximum voltage. Now odds are the minimum voltage is not going to be 0. Because of what? Because of the R of the wire. What determines the resistance of a conductor? That sounds like a good test question, right?
number 4.
What determines the resistance of a wire?
Size.
You know, the size. Length. What's that? Yeah, the material.
So you got size, you can gauge it, right?
Gauge. Gauge gets kind of flux. The gauge only applies to round wires. I've got the formula somewhere where you can calculate a flat wire. I mean, a flat thing. A lot of bus bars you see are not flat wires. They're going to be flat panels like this, made out of copper. Like the back of the panel box. So you attach your big feeds on the top, and then there's the flat gauge. And there's some way you have to take into consideration the material and the thickness, and of course the width, and then you use that to calculate what it would be for what equivalent gauge that would be, but I can't remember what it is. So gauges only deal with round wires, but you're going to run into a lot of flat conductors. And then what's the fourth thing? So we literally, and it's really accurate, guys. So metals, if you heat them up, their resistance goes up. If you cool them, their resistance goes down. So literally, we have a very accurate temperature device called an RDT, a resistive temperature device, and all it is just wire wrapped around something. In fact, that's what's usually used in your water heater. That's an RDT that sticks in the sun. We use thermocouples in ovens. And I guess we use thermocouples in refrigerators too. They might be RDTs. So these guys right here, they're gonna change the temperature. So of course that's true on almost all electronic devices. Is their specifications are given at a certain temperature. So even if you look at the resistance chart for four conductors, it's given at 20 degrees centigrade, which is like 60 or Celsius. If you look at which is about 68 degrees Fahrenheit. So it's got the same basic charge curve as a capacitor does. one-time constant, 63%, five-time constant. That should be on there too.
What?
Huh?
Yeah, where?
Should be on your, formula sheet. So one-time constant, for one-time constant, for inductors, it's L over R. And this will get you to 63%. And then to fully charge, time to fully charge would be L over R times 5. So the only thing that changes in capacitors, so capacitors or inductors are exactly opposite of each other. So capacitors it's R times C. For this is L over R because they're just what? They're just opposite of each other. So it's kind of like DC and when you're learning series circuits and parallel circuits. Just about everything you said about all these things you learned for DC, for series circuits, they were exactly opposite of it for a parallel circuit. So there's our time constant right there. L over R, V is equal to L over R. And to fully charge, it takes what? 5. So how long would it take, once I close that switch, how long would it take this to fully charge? So time fully charge would be L, would be 50 milli over 100 ohms, or 100 times 5. 500 micro. We don't. You say 0.5 milli? Okay, 2.5. I didn't hear that. Thank you. Milliseconds. I didn't hear that. Now what y'all got? Everybody got that? We okay? So how long would it take to charge this one? Fully charged would be, it's going to be 200 micro over 10 times 5. And to discharge it would be the same. So I don't know why they're doing that. Huh? We wouldn't even be able to see that. The smaller the R, the faster it charges and discharges because the smaller the R, the longer it takes to charge. I guess it's because this guy here is so small, right? So what would happen to this one if we change this to a 10 ohm? Take longer to charge. It would take 10 times that, so it should be what, 25 minutes.
What would it do if they were? I guess
it wouldn't be a time constant. Then we would have to know the resistance of the wire to calculate the time. So we could literally take an ohm meter and measure the resistance of the wire, calculate the time. So this is not going to be exact because we're ignoring the resistance of the actual R of the inductor. not millihenries. I don't know, we don't need to know that. No, okay on that. That's the same thing. Inductors in an AC circuit. Assume there's no AC current flowing through the inductor similar to an RC circuit. Ohm's law and Watt's law apply. The voltage leads the current by 90 degrees. The voltage leads the current by 90 degrees, or the current lags the voltage by 90 degrees. So we're over on what?
What are the left leads?
Well, it depends on what we're talking about. If we're talking about voltage, then on this one, voltage leads the current by 90 degrees. If it was a capacitor, the current leads the voltage by 90 degrees.
Okay.
The problem is, though, is we have series circuits and we have parallel circuits. So in a series circuit, current is constant. Right, current is constant. In a parallel circuit, then voltage is constant. So it depends on what circuit you're dealing with. Current always lags, but it can't lag in a series circuit. Because why? So that means the voltage has to be what? Leading. So, of course, on a parallel circuit, the current is going to lag. That's the same thing true over here. That's what you got to get used to. And in a series parallel circuit, guys, we're not going to get into this very much because you got to do your phase angles. You got to come up with charts. You got to come up here. And some of them go up, some of them go down. You have to subtract them out. You can't hardly do that without setting up a triangle, try to figure out the angle for the circuit. So, we'll do it just a little bit when we talk about resonant frequency and what we could do to correct the power factor. Yeah, series parallel circuits and when we start dealing with inductors and capacitors are not easy. The opposition in a capacitor is 1 over 2 pi FC. So what would you think the formula for X of L would be? And the only time we'd use that reciprocal would be if and this is why, even though they teach that, guys, and this is why I said, you know, even on capacitors, we know that capacitors in series, total capacitance would be 1 over C1 plus 1 over C2 plus 1 over C3, reciprocal sums of reciprocals. But if you can get it into opposition, then you don't have to know that anymore. All you got to know is anytime I add reactive and resistive, I have to use Pythagoras theorem.
Pythagoras theory consists of the square and the square root.
The squares of the square roots, the sums of the squares. Not it's the square root of the sums of the squares.
Yes.
So yeah, I could have come in and did that, and that only comes into play when we have multiple inductors and multiple capacitors. So what would the phase angle of the circuit be?
That would be 29.
It's going to be reactive over resistive. We can use reactive voltage over resistive voltage, or since voltage and opposition in a series circuit are directly proportional, we can use we could use 10K, we can use arc tangent of
It's R over
reactive over resistive. It says what?
It says R over S.
Not for the angle.
Angle.
You know, the angle is reactive over resistive. The tangent, I don't know, I'd have to look at the formula sheet.
Unless it's a different.
Let me look real quick.
What it changes, okay, so it changes from series to parallel.
Yeah, you're looking at parallel probably.
Okay. That's what.
Yeah, I got to be careful there. Watch out for the P and the S, right? Yeah, on parallel, current and opposition are direct, inversely proportional. So it is backwards on parallel circuit. I was going to break up my phone machine. So what did we get?
61 degrees rounded. Oh, in this case, is it like the other one will be negative? Or?
No, this is going to be a positive because we're dealing with Eli.
Okay, so it's only the IC.
Yeah. So over here is a series circuit. If current constant, so if we got if it's lagging, it's going to be negative. If it's leading, it's going to be positive. So here on a series circuit, E lags, so that angle will be negative. Over here, E leads, so it's going to be what? It's going to be a positive. That's a really good question.
Let's change it up about 5.6.
Yeah.
5.6. Notice we can drop the K. Why can we drop the K? Yeah. So it's reactive. It's the tangent minus 1 of reactive over resistive for a parallel circuit. I'm sorry, for a series circuit. Good gracious, guys.
I don't know why the equals there, but it's 10 over 5.6, and then you get the tangent minus 1.
Yeah, tangent minus 1 or arc tangent, whichever one your calculator uses. Yeah, different calculators call it different, call that angle. The angle so what we're doing here is calculating the tangent. And then we want to see the angle that's got that tangent, and that would be the opposite of the tangent. So anytime you raise any number to the minus 1, that is the opposite. And then some calculators call it the arc that has that tangent, which would be the angle. Some calculators call it the arctan. But like I said, my calculator, this calculator calls it tangent minus 1.
So that's 10 divided by 5.6.
Yeah.
And it equals 10.
No, tangent minus 1.
Yeah.
You shouldn't even have to, So 61, you got it, Adam? You got the same calculator I got, so let me break up my calculator.
Okay, mine should be the second.
Yeah, you gotta hit the second.
There you go.
You got it now?
Got now.
Good. And we can measure this one with the oscilloscope. We just have to reverse the capacitor and the inductor. $60.8 is what they came up with. So let's calculate X of L, Z, IT, VL, and VR. The power factor, the apparent power, and the true power. There's a lot of stuff we need to calculate on this one.
What do you want to start with?
Whichever one you want to start with. So I'm giving you the frequency, you got these. Here you're going to have to calculate X of L first. So the first thing we're going to have to do is X of L.
Six 6.28 kilos.
Oh yeah, 100 milliamps, yeah. 10K. I'm calling it ZT, but that's just me getting from DC calling.
This is funny. Is that, I mean, it's pretty obvious, but it's 10 kilo.
11.8.
It's got to be larger than the larger, so it'd have to be greater than 10 kilograms. What'd you get?
11.8.
Anytime y'all want to work something, let me know. Now, sometimes we do. Sometimes we get really close, but it will always be greater than it. It should always be larger than the largest, right? Anybody want to see that one work?
We got to vote in how we get turned.
The exact formula.
What'd you say?
Go ahead.
What'd you say we need?
Votes.
We need votes. How many votes y'all want to put up here?
10.
10, okay.
Strike. Still getting 10 kilo.
Good catch. So you got it now, Quinn? You get 11 points?
No, it's still holding the same thing. The exact formula shows.
Oh, let me bring up my calculator.
We got to turn.
Okay, hold on. I want to go back in here.
Oh, I see what I did wrong. Okay. No, it's not that.
You didn't hit
But
equal?
I get it, yeah. This is a stupid mistake.
Yeah, that's the simplest ones you make. But this is why we learn. This is why we learn the basic things that we know is wrong, and then we can go back and figure it out. So we know our answer's got to be bigger than 10K. Now it's going to be weird. It's not going to be the sum, but we know it's got to be bigger than that. If it comes up to be the same, if it comes up to be less, it means I've done something wrong in my math. And that gives us a chance to go back and figure it out. I mean, you probably see me do it, and I know it's wrong. I mean, I say that y'all probably heard me say it. And I cleared. I says that can't be right. Have y'all heard me say that? So anticipating what you're supposed to see, and that's the name of the game in troubleshooting, guys, is have a fairly good idea of what you're supposed to see before you put your test equipment in there. So we don't like to make measurements to make measurements. We like to make measurements to verify what we think's there. Now, if it's not what we anticipate, either we got a problem or we figure out we did something wrong. But so what you got, Quintuan?
847 microamps.
Yep. Let's see. I was asking for voltage drop.
VL. So now that we got, it's a series circuit, so now we can calculate our voltage drops. Remember, in this circuit, we're going to expect our voltage drops to be, the sum of our voltage drops to be higher than our applied voltage. And that's what you got to expect when you come in here. Back in DC, it had to equal to that.
Let's see, 8.27 for the R. Got 10 volts.
Really?
Yeah. Well, it's really 9.99.
So what we're going to do now is we're going to check our work. So when I add these two together, it should be 10, but we're going to use Pythagorean's theorem to add it. And if they don't come up to be 10, then we know we've done something wrong somewhere, right? And hopefully they showed you how to do that even in DC.
Well, something wrong.
So 8.47,
It ain't right. Something.
yeah, squared plus 10 squared equals square root. Yeah, it comes up to be 13 volts. So one of these is wrong. 6.28 times 1,000. Oh, sorry. No, I was putting resistance. I was putting opposition in opposition instead of current. So we got 847 micrograms.
Yeah. Sure. Oh, I see exactly what I did wrong. Right, that's why I hate numbers everywhere. Okay.
So the first one I came up with
Yeah, it's the L, 5.34.
5.3.
I did exactly what you did. I put 11.8 kilo instead of the other one.
And that's why it's always nice to have a way you can go back and check your work. So what do you get? 5 point what?
3. Okay.
Oh, this is 6.28K. That's the wrong thing.
It comes out as 10 volts. Right there, yeah.
What's that?
It comes out as 10 for the check the right there.
Okay, but what are we changing? What's wrong?
The volts.
This volt's right here?
Yeah.
Okay, what's it supposed to be?
5.3
Oh, okay.
volts.
Crap. So what would the apparent power be? The apparent power would be, I just take, so my apparent power would be equal to,
I thought we were doing phase angle.
we can. Let me get- So what's the phase angle? Reactive over resistive, right? Here we can use ohms or we can use volts. You should get the same angle.
32 degrees.
Everybody okay on that one? Yes? No? See it work?
You can't run that VR, you can't run VR, 8.5.
Yeah, that'd be fine. It's not gonna make that much difference. Even on a multiple choice test, it would be, I'm not gonna put a answer that's 1 decimal point off, you know.
Thank you, we appreciate that.
Even though Miss Wilson might have done that, I won't.
Oh, be a better teacher.
No, she won't. No, she's a really good teacher. She's my boss, I better say that. But yeah, she was a really good teacher. In fact, she taught some classes for us while we were doing our training. So power factor, all you have to do is just take the cosine of that, and that would be the power factor.
Of what?
The power factor is just the cosine of the angle. That's all the power factor is. You can go all day and you can take apparent power over true power. True power over apparent power, and it will come up exactly the same as the cosine.
So
If you take that 32 degrees and just hit cosine, that's the power factor.
0.84.
And some people might call it 84%. A lot of people use percentage for the power factor.
Well, I guess
Because that
it's
tells
down
you,
to
huh?
85.
Okay.
I don't think
So it's true power over apparent power, but if you look at your triangle, then it's the adjacent and the hypotenuse. They're the cosine. The apparent power is the hypotenuse, and real power is the adjacent. So that would be the angle would be the same. So you can do that. You know what I'm talking about? So if I draw the angle, then this right here is apparent power. This right over here is true power. Well, if you looked at that, that's the cosine. So the cosine is the what? It's the adjacent over the hypotenuse. And so I could do that. I could say, okay, my power factor would be equal to PR over P apparent, which is nothing but that angle. It's the same angle. So once you calculate the angle, you don't have to, you can just use the cosine of the angle. That's why I showed y'all on some motor nameplates, they call it the power factor. And some motor nameplates, they call it the cosine, because they're exactly what? They're exactly the same.
so we're going to get the true power.
True power is just the power dissipated by the resistor, and the apparent power is the power dissipated by the coil. So we can use V times I. We could use some trig. We could solve for trig, but there's no need to do that when we got those. So this right here is true power. This right here is apparent power. I'm sorry, reactive power. And then the sun, and then the
True power is 7.17.
that's the actual guide that's doing work. Now, if we've got apparent power, we could use trig to solve for the other side. But if you've got VR and you've got VL, then all you got to do is take that current and multiply it by that voltage, and that's going to give you the power. So Resistive power is true power. Reactive power is that power that's being produced by that inductor. That inductor is actually doing no work as far as electrical work does. It's got a function in life, right? You understand? It's got a function in life to respond to frequency and do something that we want to with frequency. But as far as creating watts, it don't create watts. It don't get hot. Resistors get hot. So resistive power is true power. This is the guy that actually do it. That's watts. That's what we like to pay for. We don't like to pay for that reactive power, but it has a function in life. So how would I use the device that would automatically drop the voltage down to that fluorescent bulb after it torches off? Well, if I didn't, it would burn up just like that. So over here on this guy over here, I'm using a resistor. So I forgot that one time, and of course, as soon as it glowed, it got my bulb, because as soon as that current starts flowing through that gas, as soon as the resistance of the fluorescent bulb itself drops down, which would cause the current to go up, right? You understand? Unless I have something that does what? Drops the voltage I don't want. But I don't want it to produce power. I don't want it to get hot. I don't want it to cost me power. So that's why we have ballast in those things. So these guys have function in life. I mean, they'll do things for us at certain frequencies. And like I said, one of their primary uses is for filters. Filters is when you get rid of frequencies you don't want, and you let certain frequencies pass. That's what these guys right here, that's their main use in life. Power supply, DC power supplies, we wouldn't have them without filters. Because when we go through a rectifier like a diode, we cannot get a pure DC out of that. And then, so we start filtering it to get a real good regulated DC. So we'd still be using batteries. Batteries put out a really nice DC, but they're not regulated, right? So I don't know if y'all ever loaded. If you put if you measure across like a D cell, you should measure unloaded. You should measure around 6.5 ohms. I mean 1.65 ohms, even though it's supposed to be 1.5. And as soon as you load it, what's going to happen? It's going to drop down because of the resistance of the bulb. A regulated power supply, these are electronic, which means if the voltage tries to drop down, they increase the current, right? But they can't do more than what's available to them. So it's just like your cruise control in your car. It can't do more than what it can do. So if you start going up a real steep hill, your cruise control is not going to be able to do what? It's not going to be able to maintain that speed because you've exceeded what your cruise control could do. So these are all basically the same thing, guys. A parallel. What do we do here?
Literally not connected to each other.
But here we're going to be dealing with current, right? So now we're going to move over to current is going to do what? Current is going to lag because voltage is the same. So in a parallel of RL circuit, your voltage is going to what? Your current is going to lag because your voltage is constant. And that's why this little thing, Eli the Iceman, tells you a lot of stuff of what's going on. So let's see if we can do this one. So here they've given us the values. So what would I do? So we'll probably look for IR. We can look for IL. Voltage is constant, so IR, we'll look for IL. Let me erase some of it. Gonna be volts. Yeah, there you go.
At 100 milliamps, we
could have calculated that without a calculator. Okay, what would IT be equal to?
The $111.
Okay, so let's go.
Actually, no, 112.
And how'd you come up with that?
Oh, back here.
So the sums of these current flows is more than our applied current. I think that neat.
Z.
So we can't find Z. Now that we got IT, we can find Z without, now we can use Ohm's law, right?
Yeah. 45.
So Z equals 45 ohms. That's why I learned in those, they're nice to know about that, how you calculate capacitors in parallel and capacitors in series. And all you need to really know is that capacitors in parallel go down, right? And capacitors in parallel add together, capacitors in series go down. That's basically what you need to know. And on inductors, it's just like resistors. But as far as trying to do that reciprocal of some of the, once you get these things into ohms, guys, then basically almost everything you learned in DC applies. It's just that you got to remember when anytime you add reactive and resistive, you got to use what? Pythagorean's theorem.
Why is it coming up?
What do you
You
mean?
got the milliamps for the total current.
You're not.
Well, I'm adding reactive current and resistive current, so I can't just add them. I've got to add them using Pythagorean's theorem.
That's what I.
You did use that?
What a billion come in?
It's 50 ohm.
That's the current.
That's the current, right? So 0.05 squared plus 0.1 squared equals square root. $112 milliamps. Okay, Quinton?
Yeah.
You see what you did? Yeah. So anytime we add reactive and resistive, so back in DC, we just added them together. Here, though, anytime we add reactive and resistive, we have to use Pythagorean's theorem. And that's the only difference between what we learned in DC. If we can get it in what? If we can get it in ohms.
So that's 100 squared plus 50 squared. Right?
The 100 milli squared plus 50 milli squared.
That's why in the circuit right there.
No, we're not. We can't calculate. We don't want to use that. We don't want to use. So if I was going to do that, then this is the formula I would have to use. I would have to use this formula right here. Over 100 squared plus 1/50 squared. So what we did, we solved for current. If I solve for current and if I know the voltage and I solve for current, I don't have to. I can solve for total opposition using Ohm's law. So we could have solved for it this way. So we have to use it. So it's the reciprocal of the squares of the sums of the reciprocals square. and you would come up with the same thing. It would come up and give you 45 ohms. But look at all the chances you have of making a mistake. So you'd have to put 100 reciprocal squared plus 50 reciprocal squared equals square root equals reciprocal. That's the way you'd have to enter it. But it would come up with the same answer. So what did we do?
You took the voltage and divided by it.
Divided by the opposition, came up with the current, then calculated our total current, then IT, by this. So that would be equal to 50 milli squared plus 100 milli squared. And that came up and gave us 112 milliamps. And now we got it. So a lot of people teach that thing right there, and that's fine. That's fine to use it. That's the one you want to use. But if you've got these other things, I'd much rather use Ohm's law. And that's less. So if we can get it that way, then the only thing we got to worry about is what? That guy right there. Everything else was just like we learned in DC, except now the phase angle. So I want reactive current. I want what? Reactive current over resistive current. So that's 100 over 50.
Or the exact opposite way with
Opposition. Remember, if you can use opposition, but this is parallel, and we're dealing with currents. So back in series circuit, we could use X sub L over R. Well, over here we would have to use R over X sub L, and that would be the tangent minus 1. Why? Because we're dealing with current, and current is the reciprocal of voltage, right? It's inversely proportional. So we can use it to our tangent. We can use, if I've got currents, then I can still go ahead and use reactive over. I can still use reactive over resistive. But if I want to use opposition, then it's got to be resistive over reactive. Which now you got to remember two different ways. But you should get the same angle if you do this right here.
63 degrees.
And that's up to you. But that formula is on your sheet, right? So that shouldn't be any problem. But all I want to do is understand why we reversed them. Why are we using reactive over resistive? Because we're dealing with what? We're dealing with current. And we're not dealing with voltage.
Can you hear it?
What time is it? No, we're doing really good. So let's do this one. We got everything here, right? 10 volts, which makes it easy. And we'll play around with RC circuits a little bit, guys. But LRC circuits. But as far as trying to do all the angles and stuff like that, but it's very interesting right here. And you can series parallel circuits. We're not going to get into that at all. You'd have to be really deep into electronics to get into that. But we'll definitely deal with RC, LR circuits, LCR circuits just a little bit to let y'all know why we do things the way we do.
Are you writing it down?
Yeah, wait. So what we got first?
We got the currents for our resistance.
Okay, so IR
4.54 million.
and then IL.
That one we got.
Well, let's do X sub L first. Over here I'm gonna write down X sub L. So let's do X sub L. 6.28 times 1.5 kilo times 150 milli. And don't do the reciprocal. That's what you got to remember, right? Because y'all get used to on capacitors hitting that reciprocal at the end. Here it's just a straightforward formula. 2 pi FL. I don't know, it's gotta be bigger than our big 1.4K. Okay?
Yeah.
Would you guys do this?
Huh? I ain't got anything. XBL, everybody got 1.4K?
Voltage are moving. Hard.
I did not get the same.
Wait, let's wait a minute till we,
Yeah, that's fine.
L, what we got for XBL?
That was, I forgot now.
1.4K.
Everybody okay with that? Yes, yes?
What?
1.4?
1.4?
1.4? Okay, so now we can solve for IL,
6.28.
6.28 milli.
1.5. 1 million.
You ready?
Yeah, what's IL?
I got 7.1.
Huh.
Wait, so
So it's gonna be equal to 10 divided by 1.4K. So the answer is gonna be in milli difference. So normally if you have K on the bottom, your current is usually gonna be in millions. So what we got for IL?
okay, no, I was looking back at the other equation.
What you got, Quintuan?
7.4 million.
Are we okay? Yes, no?
Oh.
Quinn? You're looking kind of weird there. You're going.
Checking myself.
We over 10, so.
Are you sure that reactance is right?
No. We'll work it though. So let me clear this out. So clear. So 6.28 times 1,500 times 0.15. 1.4K.
So what we get next?
IT. No, we get IT. We need IT before we can get. We need IT before we can get Z. Not unless you want to use that weird formula.
Oh, go ahead.
Oh, yeah, okay.
See what you did?
Yeah.
Okay. So we need IT. So we're going to have to use Pythagorean's theorem here, right? Which is a lot easier to use than that reciprocal of the squares of the sums of the reciprocal squares. So it'd be 4.5 milli squared plus 7.4 milli squared, square root of that.
Looks like it's 8.68 million.
8.7 milli good. You say 6.8? Yeah, this class, once we get them in the engineer notation, carry them out to 2 or 3 decimal points is probably not necessary. And why is that?
So far.
Nothing there.
Yeah, what's the odds of that being exactly a 2.2K?
Everything to the top.
Yeah, what's the odds of that being a 150 million?
100.
So yeah, once we get, but we need to get it in correct engineer notation. Once we get it in the correct engineer notation in this class, rounding to 1 decimal point should be fine in this class. Because what we're doing is we're we know our math is perfect, but our components are not, right? Especially if you get into transistors, guys. The beta of they give a rating on a transistor called a beta, and they give you the minimum beta. So that means that's the minimum current gain you should expect. They don't tell you the maximum you should expect. It just says you should expect the minimum. So that means one of them might have a gain of 80, and the next one right beside it might have a gain of 60, and they might be exactly the same part number. So we usually use the circuit to set the beta. So we calculate this. So okay, now we got IT. We got the applied voltage. We got total current. So now we can calculate Z using Ohm's law.
1,140.
Or that would be like 1.2 K, but this is good.
Okay.
That's fine. I mean, you gotta learn how to round with that. So the 9 would round that to a 5, and the 5 would round that to a.
I know how to round, it's just that it seems kind of high.
But if you want to carry them out, that's fine. I mean, that's fine. That's fine. So well, we got about 1.2 K ohm worth of total impedance. We got a total current of 8.3 milliamps. Even though when we add the two together, we come up with a lot more, which really confuses people in DC. So if you had 3 ammeters and you show that to the people in DC, that would freak them out. Miss Bush told us the sum of the currents have to equal to the. What else? Can we do the phase angle?
Yes.
Reactive current over resistive current, right?
We use
That's-
1.4 K.
Or you can use the, we can use, resistive opposition over reactive opposition. So you gotta switch that thing around, right? So,
It's 58 degrees.
15 degrees.
No, 58.
58.
Well, in this case, it's parallel, so it would be.
Oh, it'd be minus, yeah. Good point. Now, the only time this is really going to come into play is when we start combining capacitors and resistors in the same, when we start combining inductors and capacitors in the same circuit. Because you got to know which way to draw these vectors either to decide what the circuit's going to end up with. It's going to be more capacitive or more inductive. So if they don't cancel out, then we say if you have more C than you do L, then we say the circuit is capacitive. If you have more L than you have C, we say it's inductive. And that tells you whether you're leading or lagging, how they describe the circuit. So the power grid is as a lagging circuit. And why?
Because the voltage lead. I said that word.
No, well, the voltage can't lead. The power grid is a parallel circuit.
Yeah.
But our power grid is constantly trying to lag. And why? What's out of phase in a parallel circuit? Why do we have all these things out there? We have all these motors out there. What does motors consist of? They consist of I I brought a stator in here for you, and what it is, it's just one big old inductor, right? You understand? How many motors do we have running out there in the industry? How many motors do you think they got out of US Steel? And they're inductors. And they're trying to make the current do what? They're trying to make the current lag. So the power grid is constantly fighting a lagging power, a lagging because of all the motors we have out there. So all the motors out there are causing these things to try to lag, and that's what the power company's trying to take care of. They don't like to give you power out of phase because now their system has to support that power when most of it is not doing any work, right? You understand? It's just causing this extra current to flow through so their conductors would have to be bigger, their transformers would have to be bigger to provide power that's not even doing any work. So that's why Alabama Power charges these companies a penalty if they run a power factor less than 95%. And then they step it depending on what your power factor is. So these big companies definitely try to figure out how to monitor that power factor, right? And not only monitor it, but figure out ways to correct it. So what's one way we can correct it if it's inductors? We can add what to the circuits? Capacitors. Yeah. So if you ever went out to a big old power substation, they probably got a few capacitors, but they got to have a way to dynamically do it too, right? You understand? Because US Steel is not running all their motors at the same time. So they need some way to dynamically produce that. And we'll talk about that too. So US Steel ran a big old synchronous motor out there. And, you can actually overexcite a synchronous motor and it creates a leading power factor. And you can electronically control that. So you literally can make a dynamic power. Some of the switching stations have a switch gear that actually switches different size capacitors in. You can actually hear them clicking out there to help do what? Help manage the power factor. Synchronous motors are the most popular one. So guys, I think this is about it. We're not going to get into these get too hard to calculate.
And all changes with all RLC circuits are just the formulas.
What?
Just the formulas.
Yeah, well, and if you get them into ohms, then a lot of the formulas are what? Are the same. The only one that really changes is we have X sub C is equal to 1 over 2 pi LC. And then X sub L is equal to 2 pi FL. So one of them is frequency goes up. If frequency goes up, opposition goes down. On the other one's frequency goes up, opposition goes up. And they cancel each other out. So on series circuits, since current is constant, well, voltage over here in capacitors lag, but over here leads. So leading would go this way, lagging would go that way. So if you get these guys in the same circuit, in the same series circuit, they would, and that's where it really gets weird. I mean, you might have these guys right here might be dropping the applied voltage. So you might have 20 volts, and your resistor might be dropping 10, and you've only got 20 volts applied to the circuit, which is pretty neat. I mean, no, it would be 25. So you say you're dropping 75 volts when you only got 25 volts applied to the circuit when these things cancel each other out like that. It's really neat. So we'll look at that. We'll set up on that, but we'll come in. The first lab we'll do is going to be a class lab, and that's when we'll go over there and deal with LR time constants, and also watch me charge that thing. You saw to torch off that fluorescent bulb took 90 volts over there. So that's why I'll do that lab, and y'all come over there and y'all write down the stuff.
I think when I looked at it, we only have one more lab that we do by ourselves.
Yeah, that's the inductive reactance one. And then the LRCs will do those as classes.
And,
This is a bad one. I need to keep the bad ones out. This is probably good. The more we come up with this one, 22.7 microns.
Yeah.
In-
This is bad. So we'll charge this guy up right here. I guess I brought
Basically, I guess we'll have these two labs and then test.
huh? So what we'll do is we'll do the class lab, which I started with. And the last labs, LRC labs, we'll do as class two. So y'all only got really one lab, I'll do by yourself. It's basically the same as it's the same as the capacitor lab. We have two together here with that series. Look at one, you swap them out, so that's what you together. And look at the series.
And that's the week after next, right? That'll be a week after next week.
For you, yeah.
For him?
Adam's going on vacation.
Oh, okay.
So,
For us, we'll be doing our labs.
yeah, I'll try to record the class lab.
I can't log in and look at that.
Yeah, we'll do collaborate. Yeah, we'll do it through collaborate.
Yeah, I can log in.
You used collaborate before, right?
I don't think I have.
All you do is just, when you log into the Blackboard site, there's a link for, collaborate.
Uh-huh.
You just click on that, it'll ask you, do you want to join the room? You come into the room. So it's real easy. It's a lot like Zoom. Have you used Zoom before?
Yeah.
Except this is supported by Blackboard. And I don't have to set up a Zoom. I could do that, but I don't have to set up a Zoom thing or anything.